Now put people in timeout for different lengths, ranging from 10 seconds to 24 hours. Now put people in timeout for different lengths, ranging from 10 seconds to 24 hours. Now put people in timeout for different lengths. Just heard myself say that. Go to infinity. Okay. Got everything muted now for me. That's good. Or maybe. Okay. I'm gonna run and fill my water real fast. Now I'll get going. Go and advent a code today. A bit different from the norm CircuitPython, but we are using Python, and I figured it'd be fun to do anyway, so. All right, 1 second, let me fill up my water. Okay. We are working on, instead of the norm CircuitPython stuff, we're going to do a fun one with the advent of code for today. Haven't done today's yet. Figured I'd pop the stream on while I worked on it. If you are a person doing advent of code or wanting to do advent of code or not wanting to have Day 11 of Advent of Code 2023 spoiled, now is your chance to turn this off, because I'm going to work on it, which if you haven't yet, will probably spoil it for you. So yeah, that's your warning. If you don't want to know the answer or an answer, don't watch this. Turn it off. Thanks for checking it out either way, but yeah, don't watch. Anybody that remains is cool with seeing the answer to today's question. So I'll start with the actual question, just both to wrap my head back around it, because I read it early on this morning, and so that you all have a chance to see it if you haven't. So we are, what are we doing? We are following signs for the hot springs. We eventually get to an observatory. The elf in there turns out to be a researcher studying cosmic expansion using the telescope. He doesn't know anything about the missing machine parts. He's only visiting for the research project. However, he confirms that the hot springs are the next closest area likely to have people. He'll even take you straight there once he's done with the observation and analysis. Observation, analysis, not and, but that's fine. Maybe you can help him with the analysis to speed things up. Collected a bunch of data, compiled the data into a single giant image, which is our input, which is not so much an image as it is a big text block. The image includes empty spaces, which are dots, and galaxies, which are hashtags. Okay. Pretty good. Yep. Did I put this in small? Let's just close all this stuff. The way I've been doing it is small input for the small test one, and then input for the real one, which is really much bigger. Okay, so I think I remember what's going on here. We need to do kind of 2 steps. This is our map. Okay, researchers trying to find out the sum of the lengths of the shortest path between every pair of galaxies. Galaxies are hashtags. However, there is a catch. The universe expanded in the time it took for the light from those galaxies to reach the observatory due to something involved gravitational effects. Only some space expands. In fact, the result is that any rows or columns that contain no galaxies should automatically be twice as big. So in our example up here, we end up with 2 rows and 3 columns, which have no galaxies, they have no hashtags, and therefore they each need to be duplicated. Each row with no galaxies needs to turn into 2 rows, and each column with no galaxies, which I can't highlight as easily, but is right here, needs to turn into 2 columns. So that's our first step. Let's just do that first before we even worry about the rest. We are currently just reading the input into a string. I think this is another one where we're going to go with a string of strings. So let's go, what are they calling this? A map, right? This was a map of galaxies, data. Yeah, just data, basically, a bunch of data, pile data. Let's just call them, rows, I guess. So now we have a list of, oh well, I called it a list of lists. It's actually a list of strings, but that's fine because in Python strings behave a lot like lists. So it's effectively kind of like a 2-dimensional array. It's not really a 2-dimensional array, but it works the same way. So we need to now be able to, well, first we need to find rows and columns, but let's start with rows because that'll be simpler. We need to find rows that don't contain galaxies. Def row contains galaxy. Do this, it's going to take a row, and this one is pretty darn easy. It's just going to be if hash, dude, we don't even need that honestly. We could just say return hashtag in row. Remember, row is going to be one index, one item of rows, which means that it will be a string. Means that we can use in to test if a character is in it. We're going to return true if we have a galaxy, false if we do not. Maybe actually we should yeah, I think I'm going to change this actually. This is going to take rows instead of row, and then you're going to have to also pass a row index, which feels weird because you could just pass the string. But I think it will become clear when we get to the column one. I feel like this is going to be a little bit nicer. So rows, row index, and then our column one here, call contains galaxy, rows, column, index. Now this one is trickier. So we can't just pull out the column and do a single, is this thing in it? We need to kind of check each column basically at that index. I'm sure there is a way we could pull out the column as a string and then check it, but I don't know the way to do it. Instead, I'm going to loop. So we're just going to say for row in rows, if row call index the galaxy, then we just return true. And if we made it to the end of everything without finding one, then we know we're going to return false. Have row contains Galaxy column contains galaxy. We now should be able to say for I in this data square? No, that's, well, but it's tricky. Print length. Rows. Length of rows. Oh, okay. We are on the big one still. But it's not square. The big one. Oh, we have this though. That's why. That's fine. We're not worried about the big one right now. And 10 is square. Okay. So then we can so how do we want to do this? Because we want to add rows or columns when we find ones that don't have galaxies, but we need to make sure to not add it in front of where we are checking, because then we'll just check the new one and it will infinitely add more, which we don't want. I'm glad that I never started up the music, because I totally did desktop audio still routed through OBS, but luckily nothing made any sound. That being said, though, could go for some tunes right about now, so I think we figured this out. Okay. Doesn't really matter. I think what I'm going to do is if the row contains, so that's going to be rows, and then we'll just say I. And if it does, then what we want to do is add a new row, but we'll do it that messes us up though. If we put it before where we're at. Okay, I tell you what, let's just save a list and then add them after. So we'll say empty rows is a list, empty columns is a list. If the row does not contain galaxies, empty rows append the index. Empty rows? Empty calls, I see, okay. If not call contains galaxy rows I, then empty calls append I. Now we're gonna get a list of indexes in the original map, I'm just gonna call it a map, that don't have galaxies, both rows and columns. What is this, Matt? Empty calls? What is this? Oh. I don't know why I want to sneak that H in there. All right. Our rows indexes are, according to this, index number 3, 0, 1, 2, 3. That one looks good. And then 7, so that's 4, 5, 6, 7. Okay, we're looking good there. Columns, it says 2, so I don't know how to turn it on, but there is a select column mode. Column selection mode. 0, 1, 2. Yep, that one has no galaxies. 5, so 3 is the next one over, definitely has one. 4 has one at the bottom. 5, yep, good. And then it says 8, so 6 has one, 7 has one, 8 is empty, nice, okay. And 9 has one. So those are working. So what we're going to do now is turn this back off before I confuse myself. It's not say if it's on or off. Interesting. How do I get out of it? That's not good. Okay. Oh, boy. Oh, it does. Per file? Per file, I guess. File. Interesting. Nice. Now we're going to go back over them for empty row in for, I'm just going to say row index in empty rows. So what we want to do is add the new row in. Can we count backwards? If we count backwards, do we not run into this problem? Boy, the lights are really washing me out, huh? Oh well. If we count backwards, do we not have this problem? Yeah, I don't think we do, right? If we count backwards, we don't have this problem. Because when we add a new row at index 7, we are not going to be affecting the index of 3, but if we were to add a new row at the index of 3, we would be affecting the row that used to be at the index of 7. So if we're adding more than 2, like this, by the time we got to 8, we'd actually be off by 2, which means it would not get added in the right spot, I don't think. What we're going to go is actually for row index in, let's say, well, we know they're going to be sorted because we counted upwards when we added them, so we know the lowest ones are at the bottom. So we could just call this reversed. Go over the reversed empty rows. And then we go rows.append an empty row, which is period times the length of a row, length rows 0. Luckily all the rows are the same length. We're adding that, and we're gonna we don't want to append, actually we want to insert index object. So index is row index. Or column index. This one is a little bit trickier, just like it was when we were checking. Still not too bad. We're just gonna do a row, just do a loop in here for let's say for row index in range length rows. We loop over each row and then we add we go rows, row index. I think we can do insert on this also, right? Not, no insert for strings. I thought you could do that. You know, I guess it can't be insert directly because strings are immutable, so basically boils down to compile it together yourself. Yeah, that's fine, but it doesn't answer the question really. I don't know. Creating new strings, modifying strings. Yes, there's a difference, but at the same time, like, we still want to end up with this substring in a string at a location. New variable, same variable. I don't know. Doesn't matter so much. So we're not going to be able to insert, so we're going to have to go equals, and we basically do what they did there. So rows, row index, and we slice off call index, and then we add what we want to add, which is a period, and then we slice off the other half after call index with the thing at the end. So set it to a new string, which is everything up to our index plus a period plus everything after our index. That's going to be for each one of those empty columns. We do that. And we do it for each row when we have that column, our column index. I think that should work. So if we go print rows, we should end up with modified galaxy map. Let's go for row in rows. Print row. Have modified map to where, yeah, we have 2 rows here now that are empty. We started with just 1. Also down here. And I don't know if I can do column select in this, but pretty sure these 2 columns right here are all empty. And these 2 right here. And these 2 right here. Cool. That looks like it worked. I do think I'm going to go def expand galaxy. Maybe we should call this galaxy data instead of rows. Expand galaxy takes galaxy. That's it. anywhere left that we're using galaxy data in here? No. Okay. That should work the same, other than the fact we never called expand. So that would print the original galaxy with its 1 empty. Okay, galaxy expanded. All right. Now we need to find the shortest path between every pair. So I think we start with def find shortest path between points with lock A, location B as points, which will be X, Y. Technically, they're going to be YX, though, because I want my rows to come first, basically. So to start with, let's just hard code this to be 0, 1, 2, 3, 4. And 0, 1, 2, 0. 0, 4, and 2, 0. Zero, 4, 2, 0. Steps equals 0. Cur lock equals lock A, the starting location, while cur lock is not lock B, the ending location. So I'm just going to go really, really simple because... So in their example, they made like the diagonal path between the two, which does feel like it should be the shortest, but in this case, I don't think the diagonal helps. So they took 1, 2, 3, 4, 5, 6, 7, 8, 9 steps in order to get from 5 to 9. But instead of the diagonal path, if they had just gone 1, 2, 3, 4, 5, 6, that one, 7, 8, 9. It's the exact same number of steps if we make an L instead of a diagonal. As much as that feels wrong with hypotenuses and everything like that, it turns out to be the case, I'm pretty sure. So we don't need to worry about the diagonal, and I think it will be easier to just do each direction one at a time. So if curlock 0, which is our Y, our rows index, if our current location's row index is less than lock B. So if we are currently higher up in our two-dimensional grid, if we're higher up than where we are aiming for, we are going to take a step down. Curlock equals a new tuple, which will be curlock 0 plus 1. And then just curlock 1. So we just take one step down. If we're above where we're going, we take one step down. Also, we continue because we don't want to run any other. We want to do like one step per iteration. Also, we steps plus 1 it. Yeah. Could maybe do that somewhere else. We could steps plus 1 it right here, right? We know we're going to take a step if we're not in the place where we're going. We could steps plus 1 right there, then we don't need it inside all of these. If we need to take a step down, we set up our new current location to be 1 down from where we're at, which means that its index needs to go up. Continue. So then we're basically going to do the same thing with if we are currently below where we're trying to go. It's the exact same thing except minus. Step up. Step down. And pretty much we just need the exact same things for right and left. And then because this is inside a loop, it will just keep stepping the same direction until it gets to be in line with the target point, and then it will turn directions to step towards the target point. It will just go up, down always first, and then right, left next. It seems to me like that should also give us the shortest path. Okay, so if our current location is less than where we're going, that is actually a step right. Our current location is less than where we're going. We are to the left of where we need to be. Therefore, we add 1 here and we are stepping right. Minus that one. Is there a way to get the final galaxy location without changing the existing list? Probably. The distances, there probably is. There probably is, but I think I'm gonna change the list for mine. I think I like just growing it and then doing the count afterwards. Maybe the part 2 of the challenge might screw me over there. I don't know what the part 2 is yet, and some days you do, I guess, what I consider kind of a brute force type thing like this, where I just grow it, and it turns out in part 2 it scales up too far and it's like not feasible. That could be something I'm running face first into. But I don't know, for my brain, it's just easier to actually do the galaxy growth, galaxy expansion, and then go back and count all the distances rather than count the distance, but try to account for the expansion inside of it. But it could probably work that way. I do think it could work. Yeah, sorry as well if you put that in there a little bit ago. I had my chat covered up for a minute with OBS. All right, so we step right, step left, left, right, -1, +1. I think we are looking good there. So find shortest distance between points. So we can say that, oh, what's this? That's not what we want to do. Okay, here we go. So our distance is what? Our actual distance between those 2 points is, so if you go step 1, 2, 3, 4, 5, on your 6th step, you have reached the destination. And let's just make sure you can't go any shorter diagonal, right? So like 1, 2, 3, 4, 5, 6 is still the exact same number of steps. 6, okay. 6 steps is what we're hoping to see. Maybe 5. We might be off by 1. We can add 1 or whatever. None. None is the wrong answer. None's definitely wrong. Okay, well, we did not return steps, so that's our problem there. Return steps. 6. Awesome. Exactly what we want. Okay. Now we have a function that can count the distance between our points. So all we need to do now is get the distance from each point to every other point and add them all up. But we need to make sure not to double count anything. Okay, one thing we also need to do, which we haven't done yet, so I'm going to work on that because I'm not sure exactly how we're going to do this. I always like to work on what I know how to do. Sometimes it makes it easier to figure out how to do the stuff that you don't know how to do once you got more of the other stuff actually done instead of just knowing how to do them. So one thing we need to do is get the location of the galaxies out of our galaxy. Right. Okay. I should not have called this galaxy. Let's call this universe. And call this expand universe. And call this universe data. Yeah, because the universe contains galaxies, right? This whole thing does not represent a galaxy. Each hashtag is a galaxy. Okay, much better. Universe data. Find shortest distance. All that stuff is still the same, though. This will just use... Oh, interestingly enough, this does not actually use the map at all. Universe map. It's not doing anything like physically on the map. It's just always up 1, down 1, right? Pretty straightforward. Okay, not bad. I wonder if it's going to add rules about like you're not allowed to walk on the other galaxies or something. That might be the part 2 that's going to throw the wrench in this plan, but that's all right. All right, let's go find galaxies, find galaxy locations, find galaxy locks. From that takes a universe. It's going to return a tuple of locations, or a list maybe. Locations equals galaxy locks. For row in universe. Let's just say for row index in length universe range. Are you creating the universe? No, I don't think so. I hope not. Thank you for the question, though. I am doing the advent of code for day 11, which involves what I would call a map of the universe. They just refer to it as compiled, collected bunch of data. But it represents a location. It must, because we're counting distance between the points, so I consider it a map of a fake universe that the elves inhabit and need our help in order to get metal so that they can get sand, so that they can get water, so that they can get snow, so that Christmas can be saved. Bi-dimensional map, yeah. XY dimensions. Those dimensions? Those are, I don't know. Not really sure. All right, so we're going to loop over the row indexes, counting upwards. We're then going to loop over for call index, in range, length, universe, row 0, the first row. Loop over the rows, loop over the columns. If the character at that spot, so if universe, row index, call index is equal to hashtag, which is a galaxy, then we galaxy locks append row index. Let's see, but you'll call a file. That file is the map. You'll call a file. That file is the map. Small input. Yeah, small input. Small input contains the test input data, and then input contains the full input data. I always like to work on the test one first because I can like count stuff by hand and make sure my code is actually doing what I think. And it helps test the code because like if you get the wrong answer for the small input, then you know that you're not really ready to run it on the big input yet. And they give you the answer for the small input. So it's like you can validate that your stuff's working. Kind of. Sometimes like based on the rules, they get a little squirrely and it's like your code could work on the small one and then fail on the big one, but it's not super common. It did happen yesterday, I think, though. Let's see. So we append that. We need the call index. So we append a tuple with row index, call index. Yeah, let's do that. Let's go print the find galaxy locations of the universe data. That should give us a list of all the locations of galaxies. Instead, it gave us none. Not ideal. Seems like my problem again, though, because I have again failed to actually return the thing. That looks better. So 0, 4, 0, 0, 1, 2, 3, 4. Yep. 1, 9. That's 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Might have got an extra one in there. The thing is, yeah, I started counting after. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're on the left of it. Yeah, okay, we're good there. Those look good. Do we have 9 of them? 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. Okay. All right. So we have our points of our galaxy. We have gone to the wrong circuit. The wrong PyCharm, I mean, which is in the Circuit project. Have our locations of our galaxies. So we need to get the list of unique pairings. So given a list of things, we need to get unique pairings of those things. There are 9 galaxies in this one, correct? The chat is like trying to cover up your thing. Let's see here. Yeah, there are 9 galaxies in this one. That is correct. Yep. In the small input that we're testing right now, we have 9 galaxies. And if our distance is working properly by the time we get to the end of it, then our total will be 374. All right, so Python get unique pairings of list items. That feels like a thing there's just a function for, right? Right? Collections. Okay, thank you. Unique pairs in the list using frozen set plus counter plus list comprehension. Temp equals counter frozen set ele for ele element. Whenever I see ele like this, I think of the the lady in Jurassic Park, I think maybe he calls her Ellie, but I don't even know if that's true. For some reason, that's what it is in my brain, though. So I don't know what frozen set does, but that's saying I don't know what counter does either. Counter frozen set of element for element in test list. That's our list. So we're looping over all the elements in our list. We're passing each one to frozen set, and then we're getting, so with our list comprehension, we're getting a list of all those frozen set, whatever that is, and then we're passing that list to counter. Then next we're going result equals a list, temp, which is this one, frozen set element equals 1 for element in test list. Unique status of element is. Huh. Unique pairs list, pair dictionary. I like dictionaries. Dictionaries are pretty sweet. This might be more up my alley here. Importing. Oh, let's see. It is importing, import a counter. What even means counter? Yeah, I'm not sure. I'm not sure in Python. I've never seen count. Honestly, I don't think I have ever seen counter or frozen set that I can recall. Frozen set appears to be a built-in, and then yeah, counter gets imported from collections. But I don't know. I can't recall ever seeing either of those before. Dictionaries and lists and tuples and sorted. This looks like at first glance all stuff I'm familiar with, so I might be going this route. Find unique. So we take a list, pair dictionary equals an empty dictionary, unique statuses equals a list. For pair in list, that's our original list that we're looping over. So looping over the list, sorted pair equals sorted of pair. Okay, so sort. Ooh, sorted? Isn't that going to change the order of these? Like, so I mean, their example has 8, 9, and 9, 8, though. And 5, 6, and 6, 5. What does that do? For pair in list, sorted pair equals pair. Okay, I think that's going to I think that's going to make this one be 8, 9 instead of 9, 8. Which feels weird, but let's keep going. So tuple equals tuple of sorted pair. If tuple in pair dictionary, then pair dictionary tuple equals false. So if that sorted pair tuple is in our dictionary already, then we set its value to false. And if it's not in our dictionary already, then we set its value to true inside of our dictionary. Then we go for, so we loop over our entire list and do that. And then we go for pair in list, sorted. So we do our sorting again, we do our tupling again, and then we go unique statuses dot append pair dict tuple, return unique statuses. It is sorting. It will change the order you have. Yeah. The order of these things in the list, or the order of these individual pairs? I don't see why it would need to change the order of the individual pairs. But yeah, I don't know. I don't know why it would need to do that. But based on their test data, if their test data, oh, yeah, hold on. No. No, 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 no. This is not what we want at all. False, 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 true, false, false. I mean, with this, we could get what we want, I guess. Can we? No, this is like finding unique pairs. Finding unique. This is finding unique items. I don't really care about items. Their items are pairs, but that's not. It doesn't matter. It could be any item. Okay. Precondition. Element does not contain duplicates. We know that's the case for us, so we're cool there. Postcondition returns unique combinations of length 2 from elements. If you pass in orange, apple, banana, you're going to get back apple, orange, apple, banana, and orange, banana. Yeah, that's what we want. That's exactly what we want. I logged in. Oh, it's code review. What's wrong with the question? I mean, it should be on Stack Overflow, I guess. Yeah, it probably should be on Stack Overflow. So itertools.combinations turns out to be the answer. Itertools.combinations. Combinations. Change the coordinates. Yeah, I don't think. I guess that one. Maybe we could use the output from it to get our list, but this one I think is going to get us right there. Itertools.combinations falls under the third subcategory called combinatoric generators. Used to simplify combinatorial. That is a lot of words that not entirely clear to me. I'm just going to try to learn a little bit more about this before I just blindly copy the code. So R length tuples in sorted order, no repeated elements. Return R length subsequences of elements from the input iterable. The combination tuples are omitted in lexicographic ordering according to the order of the input iterable. So if the input iterable is sorted, all the output tuples will be produced in a sort order. We don't care about the order. Elements are treated as unique based on their position, not on their value. So if the input elements are unique, there will be no repeated values in each combination. I don't really get that last part, but this looks like it does what we want. We don't even really need the full function, honestly. And unique. Yeah, let's keep find unique pairs, actually. Let's keep the name find unique pairs. But then we just do this, and it takes in the list of galaxy locations. Let's call this galaxy locks. Galaxy locks. Import the iter tools. Whoa. import the iter tools. List combinations elements, which is now Galaxy Locks. It's just returning that, I guess. Yeah. Whoa. Unique pairs. Okay, so let's go find Galaxy Locks. Galaxy Locks equals. Then let's go unique pairs of galaxies. Find unique pairs. Galaxy Locks, print length of unique pairs. $36. I think that's what we wanted, right? Yeah, 36 pairs. In these 9 galaxies, there are 36 pairs. Okay, so we got 36. I'm not going to go look at all 36 of them, but it looks like hopefully we got the right answer. So next we loop over those. Let's just print them actually. We don't need to look at all of them, but let's do print them just to confirm they are tuples of xy. Yeah, tuples of xy coordinates. Okay, so now we go for pair, 36 pairs in total. That should mean something like 300 and something else. Yeah. Yep, 56 or 46 or something like that is what they got for the test input. So for pair in unique pairs of galaxies, distance equals find shortest path between points of pair 0, pair 1. Total distance equals 0. Total distance plus equal distance. Print total distance. $374. Sounds high, but maybe I was. Nope, that's right. Nice. Okay, 374. Yep, I was just misremembering. Okay, so we got the right answer. We should be good. We should be good. Now we try it on the real input. And we hope that there's not a big enough scale that it just can't finish. All right, let's go to here. Nice. Sweet. We are 1 gold star closer to restoring the snow operations. All right, let's get a look at part 2. I don't know for sure if I'll sit here and do it right now, but let's see. Galaxies are much older and thus farther apart than the researcher initially estimated. Now, yeah, see, here's where our, here's where our scale is probably going to wreck us, huh? Instead of the expansion you did before, make each empty row or column 1,000,000 times larger. Each empty row should be replaced with 1,000,000 empty rows. And each empty column should be replaced with 1,000,000 empty columns. In the example above, if each empty row or column were merely 10 times longer, the sum of the shortest paths between every pair of galaxies would have been 10 and 30. If each empty row or column were merely 100 times, then the sum of the shortest paths would have been 8410. However, it will need to expand past that to 1,000,000. Starting with the same initial image, expand the universe according to these new rules, then find the length of the shortest path between every pair of galaxies. What is the sum of these lengths? All right, so we probably can't. Let's see what we have. 140 by 140. Is that our size? Still printing our size. We printed too many pairs to be able to see anything else. Yeah, we are still printing the size up there. $140 by 140. Okay. Well, is that too much to brute force? So, I mean, we only have 1, 2, 3, 4, 5, 6 rows and 2 columns. It's probably too much, isn't it? I think it's probably too much. And in any case, we'll learn more by doing the solution that's not brute force. So we need to, instead of actually expanding the universe, what we could do is just keep these lists of rows or columns, and then inside of distance method, don't. Hey. Stop. So basically we could just make it whenever, so in here we could just make it if you're about to step down onto, i.e. meaning if this number is equal to any of these numbers in our empty list, then what we do is we no longer step 1, instead we step 1,000,000. And then our actual map doesn't actually expand, but our steps will account for that number without having to loop it. Buddy, seriously, stop. Make the biscuits. Okay. So what we are going to do is we're going to take all of code, we're going to bounce over to code 2, we're going to erase all that, we're going to put all this in here. We're just going to get rid of this because we're not even doing images in this one right now. All right. So now we're going to say this function's going to change to be lock A, lock B, X expanded rows, expanded columns, and then also expansion factor. So new y equals if new y is in the expanded rows, we want to add, so if we keep this right here, then what we want to do is add 900,999 so that way our total would be 1 million. We do not want to change our cur lock, which is awkward because we're moving one point on our map with our cur lock, but steps is what we actually care about. So as long as we account for it, then it should be fine. So let's say if new y is in expanded rows, then we're going to go steps plus equals. Okay, yeah, we'll just go 9999. It's like I kind of want to do 1 million minus 1, but 9's here. Steps plus equals that. Okay. And basically the exact same thing here. Except new y is different. New y. All right, so if we're about to step on a place that has been expanded, we actually take 1 million total steps in the vertical direction. For our horizontals here now, we go new x, new x. If new x in expanded columns, then we go steps plus equals our 9 and 9's. Last one, new x equals all right, and let's drop ourselves back to the small input. Let's not do the expansion. Expand universe. We don't want to do that. We can still print, that's fine. We still need to find the galaxies. We still need to get the unique pairs. Total distance, everything else should be good. We do need to pass in now our expanded rows and expanded columns, which we don't have. All right, so what we need to do is maybe let's have one called def get expanded rows and calls. And then here we could say empty rows, comma, empty calls equals get expanded rows calls universe. Call them expanded instead of empty. It doesn't matter really, I guess, but we need to return them. Return expanded rows, expanded columns. Empty T, empty P, empty T. We'll jacked this up, huh? Okay, there we go. Okay. So now we're back to not wanting to expand, but we can reuse that part of it by saying expanded rows, expanded calls, get expanded rows calls universe data. Now we can pass expanded rows, expanded calls, expansion factor. They said if it was 10 times, it would be 1030, so let's call it 10 times. Oh, okay, here's what we should do is expansion factor. This should be expansion factor -1. That's what that should be, in fact. We don't need the 9s. So we'll pass in 1 million when we want to go to the 1 million expansion factor. There we go. Okay, now we have 10, so if this works, we should get 1030. We are on the small input. Nice. They said also if it was 100, that would be 8410. Let's check that too. Oops, accidentally did debug. That's so totally not what I wanted to do. Okay, let's just try that with a regular old run. 8410, nice, good to go. So, expansion factor of, well, they didn't tell us 1 million on, they did not tell us 1 million on the small input, so we'll just go 1 million on the big input. Hope that we don't crash the computer or anything. $1 million. Let's just check 1 million on the small. Nice. 820000210 on the small. Okay. Swap that out with the big input and moment of truth. Nice. We got that pause there. I was a little worried for just a second, but yes. All right, we got it. We are closer to restoring the snow operations. All right. I think that's it for now. Thanks for hanging out. Werg Sirium over in the YouTube. Thanks for stopping by, chatting it up. If you're interested in programming streams, feel free to give me a follow or subscribe on YouTube here. Typically, I work on a project called CircuitPython. If you don't know what that is, you can learn more at circuitpython.org. This is basically a version of Python that runs on microcontrollers instead of on big computers. So these tiny little computers on their little devices that come in all different shapes and sizes and different kinds of hardware that can connect up to them. So if that kind of thing sounds interesting to you, feel free to subscribe. I do other kind of unrelated stuff like advent of code like we did tonight, less frequently, but still from time to time. Thanks also to Blooming Code over in Twitch if you're still around, my friend. Thanks for stopping by, hanging out. And yeah, I hope everybody has a good day, good night, good rest of your week. I'll be back on Friday for the deep dive this week. So Friday at 4 p.m. Central, 5 p.m. Eastern, 2 p.m. Pacific. Those are all U.S. times. That's over on the Adafruit channel. And I'll be back on Saturday as well on my channel here, 10 a.m. Central on Saturday. That's my kind of weekly recurring one. So that's usually when you can catch me working on CircuitPython is Saturday mornings, 10 a.m. Thanks for hanging out, everybody. I will catch you next time.